Hello, mathematicians. In this video, we will discuss the logic of quantified statements. Now, there's a lot of reading in this on these slides, and so I really want to encourage you to take the time to pause the video when necessary to think through some of these examples and process them and make sure they make sense to you. A lot of this is going to be translating from symbols, formal mathematical language to informal language and vice versa. So we begin with a definition, a predicate. It's simply a sentence that contains a finite number of variables. It becomes a statement when specific values are substituted for the variables. And we get those values from a domain. The domain is all the possible values that may be substituted for the variables. And surely domain is not a new concept to you. So we let P of x be the predicate. X squared is greater than x. So we see that this has a finite number of variables, namely 1. And the domain is the set of real numbers, all real numbers. We're going to find P of 2, P of 1/2, and P of negative 1/2. So this predicate is going to become statements when we substitute these values, and we can indicate if the statements are true or false. So here we have the values substituted into the predicate. They are now statements, which can now be determined to be true or false. So we see that when we substitute 2 or negative 1/2 into the predicate, we have 2 true statements. However, that middle example of 1/2 makes the statement false. The truth set is going to be all of the values in the domain that, when substituted into the predicate, make a true statement. So let's consider the predicate n is a factor of 8. Find the truth set of Q of n if the domain of n is z plus, meaning all the positive integers. So we want to take all the positive integers and figure out which ones, when substituted for n, will make this a true statement. And I think it is pretty easy to see that of all the positive integers, 1, 2, 4, and 8, when substituted in place of n, would make this a true statement. 1 is a factor of 8. 2 is a factor of 8. 4 is a factor of 8. 8 is a factor of 8. And so what I have written here is the truth set. Now, in part B, we're opening up the domain to be the set of all integers, not just the positive integers. And so we would include all of the negative values for n that would also be true. We know that negative 8 is a factor of 8. Negative 4 is a factor of 8, and so on. And so we can expand our truth set to include the negative factors of 8. And this page just says that a little nicer. Okay, let's talk about the universal quantifier. It looks like an upside down capital letter A. One sure way to change predicates into statements is to assign specific values to all of their variables. For example, if x represents the number 35, the sentence x is evenly divisible by 5 is a true statement, since 35 is equal to 5 times 7. Another way to obtain statements from predicates is to add quantifiers. Quantifiers are words that refer to quantities such as some or all, and tell for how many elements a given predicate is true. This symbol is called the universal quantifier. Depending on the context, it is read for every, for each, for all, given any, or for all. For example, another way to express the sentence, every human being is mortal, or all human beings are mortal, is to write the universal quantifier symbol, human beings, X is mortal, which you would read as, for every human being X is mortal. If you let H be the set of all human beings, then you can symbolize the statement more formally by writing, for all X in H, X is mortal. Let Q of X be a predicate and D the domain of X. A universal statement is a statement of the form, for every X in D, Q of X. It's defined to be true if and only if Q of X is true for each individual X in D. It is defined to be false if and only if Q of X is false for at least one in D. A value for X for which Q of X is false is called a counterexample to the universal statement. In other words, to show that a universal statement is true is to show that it's true for every value in the domain. To show that it's false, we only need to find one example where it is false. Just one element in the domain for which Q of X is not true, that would be our counterexample to the universal statement. Here we set our domain to equal the integers 1, 2, 3, 4, and 5, and consider the statement, for every X in D, X squared is greater than or equal to X. Write one way to read this statement out loud and show that it is true. So I've already read it. To show that it's true, we would actually need to take each of the values, starting with 1, and show that 1 squared is greater than or equal to 1. Certainly that is true. 1 squared is equal to 1, which is equal to 1. We would show that 2 squared is greater than or equal to 2. Certainly 4 is greater than 2. We would show that 3 squared is greater than or equal to 3. True. 4 squared is greater than 4. Yes. And 5 squared is greater than 5. Since we have shown the statement is true for every element in the set of the domain, then it is a true statement. In part B, we're considering the statement for every X in R. Remember, R is the set of all real numbers. X squared is greater than or equal to X. Find a counterexample to show that this statement is false. So changing the domain of the predicate makes all the difference here, or of the statement. Okay, for every X in R, I can show that there is an X in R for which this is not true. Namely, I can say, what about if X is a fraction, such as 1/2? 1/2 squared is 1/4, and that is not greater than or equal to 1/2. This is a false statement. Therefore, X equals 1/2 is a counterexample to show that the statement is false. And this slide just says that in a more lovely way. Okay, so we talked about the universal quantifier. Let's now discuss the existential quantifier. It looks like a capital letter E backwards. And it simply says that there exists. For example, there is a student in Math 140 can be written as, there exists a person P such that P is a student in Math 140. Or more formally, there exists a P in capital P, such that P is a student in Math 140, where capital P is the set of all people. The domain of the predicate variable is generally indicated either between the there exists symbol and the variable name, or immediately following the variable name. And the words such that are inserted just before the predicate. Let Q of X be a predicate, D is the domain. An existential statement is a statement of the form, there exists an X in D, such that Q of X. Now, an existential statement is simply saying that there is at least one. So it is defined to be true if and only if Q of X is true for at least one X in D. And it's false if and only if Q of X is false for all X in D. So this is very different from the universal quantifier. To show that an existential statement is true, we simply need to show that there is at least one element of the domain that would make the statement true. To show that an existential statement is false, we have to show that it is not true for every element of the domain. Okay, so let's take a look at this statement. It says, write one way to read this statement out loud and also show that it is true. It says there exists an M in the element of positive integers such that M squared is equal to M. So to prove this is true, we simply need to find at least one value for M in the set of positive integers that would make this statement true. And certainly, if we allow M to equal 1, then 1 squared equals 1 is true. So we found that at least one number exists among the positive integers. In the next example, it says, let E equal the set 5, 6, 7, and 8, and consider the statement, there exists an M in the set called E, such that M squared is equal to M. Show that this statement is false. Okay, we're saying that there's at least one number in the set called E, such that M squared is equal to M. To show this is false, we must show that it is false for every element in E. Certainly, 5 squared is not equal to 5. What about 6 squared? Is it equal to 6? Nope. 7 squared is certainly not equal to 7, and 8 squared is not equal to 8. So this is very different from the universal statements, because universal statements, we must show that it's true by showing it's true for every element. And to show that it's false, we must show that it's false for only one element. And you see here for the existential statements, it's exactly the opposite. To show that an existential statement is true, we only need to show that it's true for one value. To show that it's false, we must show that it's false for every value. So take a moment to process that and make sure that makes sense to you. Okay, so this is going to be a lot of reading, and so I just encourage you to take some time to read through this formal versus informal language. There is not one correct way, one letter by letter right answer for some of these. So the spirit of the sentence needs to be upheld, but please don't hold yourself to the exact wording or phrasing of some of these. It's very important that we can translate formal and informal language with symbols, just informal sentences, mathematical symbols and statements. And so that's what this section is about. It says rewrite the formal statements in a variety of equivalent but more informal ways. Do not use the symbols for all or there exist. Do not use the universal quantifier or the existential quantifier. As a matter of fact, I encourage you to try to write these sentences without mathematical symbols at all. Pause this video and see if you can do that. Let's see how you did. So the first one, we can say very informally, every real number has a non-negative square. Okay, so that's another way of saying greater than or equal to 0. We certainly can't say positive. Positive does not include 0. 0 is neither positive nor negative. So if we want the numbers, if we want to say something is greater than or equal to 0, a nice informal way of saying that is saying that it is non-negative. And as you can see, there are a few variations, and you may have even said this a little different, and that's okay. These are just some of the ways you could translate the mathematics, the formal mathematics, into an informal sentence. Part B, all real numbers have squares that do not equal -1, or no real numbers have squares equal to -1. So the words none are or no are equivalent to the words all are not. So with the English language being what it is, sometimes you have to phrase things a little differently to make them make sense in the English language. But the the formal language should look very much the same. And finally, example C, there's a positive integer whose square is equal to itself. Or we can find at least one positive integer equal to its own square. Or some positive integer equals its own square. Or even some positive integers equal their own squares. So again, the spirit of the formal statement should be preserved, but there you have a lot of leeway into exactly how you're going to say that. Rewrite the following statements so that the quantifier trails the rest of the sentence. So they're just wanting you to say this in a different way, where the for any appears after the quantifier. There exists appears after here. So I don't want to take a whole lot of time on this, but these are just alternate ways of saying, for any integer n, 2n is even, can also be said like this. 2n is even for any integer n. Okay, so the quantifier might come after the rest of the sentence. All right, there exists at least one real number x such that x squared is less than or equal to 0. Or x squared is less than or equal to 0 for some real number x, or for at least one real number x. Just alternate ways of expressing the same information. Rewrite each of the following statements formally. Use quantifiers and variables. If you like, you can pause this video and try it yourself. Try to use the universal quantifier and the existential or the existential quantifier in these statements. So here are just some examples of how you could say this. Again, using the universal quantifiers and the existential quantifiers. And I'll give you just a moment to kind of read through this. So mostly in practicing writing formal and informal mathematical statements just requires you to just more practice, examples, looking back at things that have already been written and trying to model your statements after those. Okay, so universal conditional statements are something like this. For every x, if P, then Q. So here's an example. For every x that's an element of the real numbers, if x is greater than 2, then x squared is greater than 4. Think about how you might express this idea in an informal sentence. Here are just some examples. If a real number is greater than 2, then its square is greater than 4. Or whenever a real number is greater than 2, its square is greater than 4. I like the last one. The squares of all real numbers greater than 2 are greater than 4. So all of these convey the same information in a much more informal way. Okay, rewrite each of the following statements in the form for every blank, if blank, then blank. So the first one says, if a real number is an integer, then it is a rational number. Think about what you would substitute into those blanks. Again, pause the video if you want to give it a try. Then you can repeat the process for the next two statements. All bytes have 8 bits, and no fire trucks are green. Let's take a look. For every real number x, if x is an integer, then x is a rational number. Or symbolically, for all x in R, if x is in Z, then x is in Q. This R represents the real numbers, Z, the set of integers, and Q, the set of rational numbers. Part B, for every x, if x is a byte, then x has 8 bits. Part C, for every x, if x is a fire truck, then x is not green. It is common, as in Part B and Part C above, to omit explicit identification of the domain of predicate variables in universal statements. Okay, for every x, if x is a fire truck. So that is indicating that the domain is the set of all fire trucks. Part B, for every x, if x is a byte. Well, that must mean that the domain is the set of all bytes. Equivalent forms. Observe that the two statements for every real number x, if x is an integer, then x is rational, and for every integer x, x is rational, mean the same thing because the set of integers is a subset of the set of real numbers. So we didn't need to say that x was a real number if we're saying x is an integer. Because if x is an integer, we know it already is a real number. Both have informal translations. Okay, so in fact, a statement of the form, just like this, can always be written in this way. So we can simplify this. By narrowing the universal set to be the subset D consisting of all values of the variable x that make p of x true. We can simplify our statement. Conversely, a statement of this form can also be written in the other form. Rewrite the following statement in the two forms. For every x, if blank, then blank, and for every blank x, blank. So the statement is all squares are rectangles. Once again, I encourage you to pause. See if you can fill in those blanks properly. Let's see how you did. We could say for every x, if x is a square, then x is a rectangle. Or we could say for every square x, x is a rectangle. Both are great ways of saying the same thing. A prime number is an integer greater than 1 whose only positive integer factors are itself and 1. Consider the statement, there's an integer that is both prime and even. Let prime of n be n is prime, and even of n be n is even. Use the notation prime of n and even of n to rewrite this statement in the following two forms. There exists an n such that, and there exists blank n such that blank. Again, using prime of n, remember what prime of n means. It means that n is prime. And even of n, which means n is even. See if you can plug those properly into these sentences. Let's check it out. There exists an n such that prime of n and even of n. Part B has two ways. You could say, there exists a prime number n such that even of n, or there exists an even number n such that prime of n. Again, try not to get too bogged down in these. I know this is a lot of technicality here, but really it just takes practice to be able to take a formal mathematical symbol and understand what it means informally, and vice versa. When you see a statement informally and you need to write it in a formal mathematical way, it just takes practice. It takes having some templates to look at, some good examples, some good models. All right, so here we have a statement for every integer x, x squared is greater than or equal to 0, and there exists a real number x such that x cubed is equal to 8. Now, both of these statements call the variable x, but they serve different functions. Okay, they're not the same x. So we say that the variable x is bound by the quantifier that controls it, and its scope begins when the quantifier introduces it and ends at the end of the quantified statement. Okay, so x is bound by the quantifier that controls it. But after the statement is over, then that's the end of that. So when you move on to a different problem, the x from the previous is not the same, which I think you probably realized in your algebra class. In problem number 1, if x was equal to 2, then when you move on to problem number 2, you still have x, but that doesn't mean that it's equal to 2 anymore. Okay, so we can have that. What we've seen so far is very explicit use of the quantifiers, but they could also be implicit or implied. So consider this statement. If a number is an integer, then it is a rational number. There's nowhere in this sentence that we see for every or for all, but it is implied. If a number is an integer, implies that we're talking about all integers. Okay, so sometimes we have implicit quantification. So this is certainly a universal quantification, even though it doesn't explicitly say that. Existential quantification can also be implicit. For example, let's suppose we say the number 24 can be written as a sum of two even integers. Again, nowhere in here does it say anything about there exists, but we can imply that there exists some integers m and n. There exists some even integers m and n, such that 24 is m plus n. So, long story short on those, quantified statements can be explicitly stated or implied. Okay, we have some notation. P of x and Q of x are predicates, and the common domain of x is D. The notation P of x and then this double arrow means that every element in the truth set of P of x is in the truth set of Q of x. Or equivalently, for every x, P of x implies Q of x. Now, if we use a double-sided arrow, it simply means that P and Q have the identical truth sets. So you can kind of think of this first bullet as a subset. The truth set of P of x is a subset of Q of x. And then in the second bullet point, the truth sets are the same. All right, so we have three predicates here, Q of n, R of n, and S of n. Q of n is a factor of 8. R of n is a factor of 4. S of n is less than 5 and n is not equal to 3. Suppose the domain of n is z plus, the set of all positive integers. Then use these symbols to indicate the true relationship among these. So again, think about the truth sets of Q of n, R of n, and S of n. So for Q of n, we've already talked about the truth set is 1, 2, 4, and 8. For R of n, if n is a factor of 4, that's going to be 1, 2, and 4. Now S of n is less than 5, and n is not 3. So we would have 1, 2, 4. So we can see that some of these sets are the same, and some are subsets of others, okay? And so we could write that, let's just go back and write it here. So I can see that R of n and S of n have the same truth set. And R of n its truth set is a subset of the truth set of Q of n. So I would say R of n and then just use a one-sided arrow, and S of n and a one-sided arrow. And this is just explaining this in a lot more words.